Okay, let's start. So in the previous class, we learned about cache organization. So actually, so you can just remember the definition of cache. That means the purpose of the cache. So as I mentioned, the cache is the small memory component. Then because the size of the cache is small, and then as I mentioned, cache is located in the CPU chip. And then we use SRAM, the static RAM technology for organizing cache. So which means that the cache performance is the higher the DRAM. So which means that the main memory of the computer system. So the problem is that because the cache size is smaller than the DRAM, then we need to store the frequently accessed data in the cache. Also, we need to identify which data is stored in the cache. So in order to identify the data in the cache, we also store the tag. Okay? Tag. So actually you can identify different data using address. So when the data is stored in the cache, we just store the part of address, because we can use the part of address for index of the cache. Okay, so we just store the part of the address. So this figure shows the example cache organization. Okay, so also as I mentioned that cache has multiple entries. Cache has multiple entries, right? And then each entry has the specific size. So which means actually, so think like this: when the load instruction is executed, such as the load word, and the load word is executed, the processor requests word size data. It's the 4-byte data. Okay, but we can compute any size of the block of cache. So which means that we can compute the cache block size as 4 bytes. It's 1 word. Also, we can also use the large block. So which means that the cache block size, the size of a single cache block, can be larger. So which means maybe 64 byte. Okay, so we can compute the cache block size also. So what does that mean? So cache is the memory component. So then the memory component has multiple entries, and we can also store our data in the certain entry of the memory component. But when this data is accessed from the memory component, then we can just access the 1 block, the block granularity. So which means that we can just access the certain block of the cache using the address, and then I said this address is called the index of the cache. Okay, so we need to distinguish the address of data and the index of the cache, because the cache has the multiple entry, and then actually we can access a certain entry or certain block of the cache using the index. Okay, so when we access a certain block of the cache using an index, then the entire block is read from the cache. Okay. Also, data is stored. So which means that I said in the previous example, when the load instruction is executed, the data is requested from main memory, right? The data is requested from main memory, and if the data is not found in the cache, then data should be transferred to the cache. Okay, So which means that the cache block size is larger than the, so it can be larger than the requested data size. So in this example, we assume that the data size is word, so it's the same to the word data size, but the cache block size can be larger than a word. Okay, so in this example, it's a 64 byte. Okay, so which means that when a load word instruction request word size data, the 4 byte data. So this data size is smaller than the 64 bit, so 64 byte cache block size. So in this, so when this data is requested by load instruction, then entire block. So in this example, 64 byte, which is equivalent to the cache block size. So entire block is transferred to the a certain block of the cache. So in this, so you need to remember, even though actually in chapter 2 we learn the different kinds of load instruction, like the load byte, load half word, load word, also load double word. So actually, these different load instructions request the different size data, but when a certain data is requested by load instruction, entire cache block is filled with the data from memory. Okay, so even though the 24 byte data is requested by a processor, and if this data is not found in the cache, then the processor fills the 64 byte of the data, so which is equivalent to the one cache block size. Okay, so and then we can access the cache using the index and then the address of the requested address. So I will explain using this example. So in this example, actually the address size is issued with 32. So actually in the second edition of the book, actually in the first edition of this RISC-V book, actually we handled the 64-bit computer system, but in the second edition book, we are handling the 32-bit computer system, which means the address, the size of the address is the 32 bits. Okay, so it should be 32, and it should be 31. So in this example, you can find the byte offset. So what does that mean? Actually, we can access the cache using the index. Okay, so and then this is the direct map cache. So we just use the lower 10 bit of the address. But as you can see, we can find the 2-bit byte offset. So which means that this byte offset represents the size of a single cache block. What does that mean? Cache is accessed by this index field. Okay, so and then as you can see, in the address field, index field occupies the pin number 11 to pin number 2. So we use the 10 bit for the index of the cache. So this question, so how many blocks can be found in the cache? We use the 10 bit for the index field. So how many blocks can be found in the cache? Right. We can find 1024 blocks in the cache. So this is the direct map cache. So as you can see, using the 10 bits of index field, we can identify index number 0 to index number 1023. So which means that this cache has 1024 blocks. Okay, and I said, well, this index field starts from the address bit 2, and then this is the byte offset. So what does that mean? In chapter 2, I mentioned that most computer systems actually all most computer systems use byte address. So which means that address 1 represents the 1 byte of data. But when the cache is accessed using this address, so we use the lower 10 bit, but it's this index field starts from the address bit number 11. So we use the last 2 bits, the lower 2 bits as the byte offset. So which means this byte offset represents the size of block. So it means a single block of cache occupies 2 bits of the address field. 2 bits of the address field. So it means a block size is the 2 to 2. It's the 4 byte. Okay, understand? Okay. So using this information, then you can calculate the size of a cache. How? So cache has the 1024 blocks, and then one block size is the 4 bytes. So the size of the cache is the 4 multiplied 1024. It's the 4 kilobyte. 1024 is the kilo in the computer system. Okay, it's a 4 kilobyte. And but in the address field, the address field starts from the pin number 31. So which means that we can use the 32-bit address for accessing data to the main memory. And then index field occupies until the address bit 11. So how can we identify the data in the cache? We need to store the address of data to this cache, but we can use the lower 10 bit for the index field, and then also we can use the lower 2 bit for the byte offset. So which means that the block size is larger than the 1 byte. So actually, we can use the lower 12 bit, so in number 11 to 0, as the index of the cache and the byte offset of the cache. So which means that we don't need to store entire address field to identify data in the cache. So we can just store the remaining bits of the address field to identify data in the cache. So we can use this field as tag. Okay, the tag of the cache. So because the address field, the size of the address field is 32-bit, then we use the lower 12 bits for the index field, and then by the offset of the cache, then we can use the address bit 31 to 12 as the tag of the cache. So it should be 20. Okay? So it bits. So this is the cache organization. So as you can see, as I mentioned, the cache is the memory component. Okay, and then we also figure out size of the cache block or single cache block is the 32-bit because it occupies the 4 byte. Okay, so if you see this cache organization, so you can find that So it's a control bit, it's a valid bit. So I mentioned in the previous class, we need to also check the validity of the stored data in the cache. So we require the valid bit. Okay, so like this, I also explained about the valid bit of the cache, and this cache also stores the tag. In this example, the tag size is the 20 bit, right? And then the cache also stores the data. Okay, so data is the cache block size is the 4 byte. So we just store the 32 bits of data in the cache. So this is the cache organization. The one entry. This is the one entry of the cache. One entry of cache stores the data because the data is to be stored. And tag. Not identify data, so we need to also store the tag. And then we also store the control bits such as the validity here. So this is the example of cache organization.
아이트 없을 때는 어떤 값이든 상관없이 버려지는 거예요.
버려지진 않고요. 만약 우리가 이제 로드 워드 했다고 하면은 32빗을 다 사용할 거잖아요. 근데 만약 로드 바이트 뭐 LB를 썼다 하면은 뭐 캐시에서는 이제 블락 단위로 이제 액세스를 하니까 원 블락을 다 읽어오긴 하는데 그 중에서 또 선택을 해야 되잖아요. 로드 바이트 그럴 때 이제 쓰이는 거죠. So actually there are different kinds of load instruction, like load helper or load bind, and then we can use this byte offset field to identify the request data by the different kinds of load instruction. So for example, so if the load byte is requested, then as I mentioned, the cache is accessed in the granularity of block. So the entire block is read from the cache, but load byte just request 1 byte of data. So among these 4 bytes of data, then we need to select which data should be transferred to the register file of the processor, right? So we can use the byte offset for this proposal. Okay. So I will explain about the operation of the cache. So this is the cache organization. So let us assume that we are the processor requests a certain data using the load instruction. Okay, so it's 32, it's 20, it should be 20. So let us assume that the load word instruction is request the data data A using the address. So let us assume that the address of the request data is A. So then this address is the 32-bit address, right? So we can use this address field to identify the requested data. Then if the processor requests data using the address A, then this request is given to the cache first, right? Because we need to first check if the request data exists in the cache, right? So using this address, then, but in order to check the cache, we need to also figure out the index field of the cache, also tag of the cache. So this address is split into the tag part is the address 31 down to 12, and then index part, address 11 down to 2. So using the tag and index, then the processor access the cache. So first we access cache using the index. Okay. So index is let us assume that the index field is the 64. Then using this index, then processor check the delete, tag, and read data of the cache. Okay. So index is the address of the cache. So which means that if this index is given to the cache, then we can read the stored data. So which means that delete field, tag, and data, the stored data, the cache. So we can read this data. Then we need to check this cache stores the request data or not. So in order to check the request data exists in the cache or not, then we need to compare the tag, right? So first, using the index, this entire cache block, cache line is read from the cache, and as you can see, the tag, the size of the tag is the 20-bit. Using the address, the tag of the address, and then the processor just compare the tag of this request address and the tag stored in the target cache block. Okay, so you can find that. So you can find the comparator here, right? Also, we need to check that if this stored data is valid or not. Okay, so we can check the validity of this data using the validity. Okay, so you can find the comparator here, and then you can find the AND gate here. So, and the one of the input is connected to this valid field, valid bit, and then another input of this AND gate is connected to the output of the comparator. So if the valid equal 1, and then if the tag is equal, so tag of this address is equal to the tag stored in the cache, then it should be 1. So which means, oh, it's 1. The output of this AND gate becomes 1. So this means the cache has the requested data. So data is valid, and then tag is the same, which means the request data can be found in the cache. So this event is called the cache hit. Okay. So if this output is 0, so which means that the data is not found in the cache. So this event is called the cache miss. Okay, if the cache is hit, then this data, the stored data, can be provided to the processor, right? So we can read data from the cache quickly, and then so we can reduce the required latency for data. But if this data is not found in the cache, so which means that the output of this AND gate is 0. Okay, so which means that the target cache block does not have any valid data. So or the tag, if the tag is different, the tag stored in the cache is different from the tag field of the address. So which means that this cache does not have requested data. Okay, it's a miss. It's cache miss. So what then? Cache request the required data. So the 4 byte of data. So the size of the cache request is equivalent to the size of a cache block. So in this example, the block size is the 4 byte. So in this case, cache request is 4 bytes of data to the low level cache or main memory, right? If this cache is the multi-level cache, like L1, L2, and L3, then if the cache is the L1 cache, then request is given to the L2 cache. But if this cache is not multi-level cache, then we can find the memory. Okay. Then if the cache miss is detected, then the request for this 4 bytes of data is given to the memory. Okay. Then if this request is given to the memory, and then let us assume that the next level is the main memory, then we can find the data because the main memory has the data. Okay. So if this request is given to the memory, and then memory becomes the 4 bytes of data to the cache, and this data is stored. So this event is called the cache allocation. So this data from the memory allocated in the target cache block. So after this allocation, then we can find the request data in the cache, right? Because the data is stored in the cache. Then this data is read from the cache and then even provided to the processor. That's how cache miss is handled in the processor. So cache hit is the good case. Unfortunately, it means that the request data is found in the cache. So cache can provide the request data to the processor. But if the request data is not found in the cache also requests the one block of data to the low level cache or main memory, and first allocate this data from memory or low level cache, and then provide the request data to the processor. So in this case, the data is provided by low level cache and the main memory, as I mentioned. So it just loaded its current level of the cache. So it will take many cycles. Okay. So this is the behavior of cache. Okay.
블럭을
네.
에미드랑 태그는 블럭이라고 생각하는 데이터 있는
보통 우리가 이제 블록 사이즈라고 하면은 데이터만 많이 확인합니다.
그리고 그 미스가 났을 때는 그러니까 데이터를 읽는 과정에서 L1을 보면서 동시에 L2를 같이 읽는 거예요.
그렇지, 그렇게 하진 않아요. The firstly L1을 체크를 하고 그 다음에 L1에서 미스가 나면 다시 또 리퀘스트가 L2로 가는 거예요. 네. 왜냐면 이게 이거 리퀘스트 자체도 리소스, 그다음에 컴퓨터의 버스를 상황하는 거거든요. 모든 리퀘스트가 다 L2까지 가면 L2가 또 동작을 해야 되기 때문에 그만큼 리소스가 소비가 돼서 한번 L1을 체크를 하고 L1에서 이제 미스가 나면 L2까지 다시 가는 거거든요. 그러니까 단계는 안 되는 거예요. Good question. So as I mentioned, that when a cache is organized, then we can also assign several bits from the address. So tag of the cache and the index of the cache and the offset of the cache. That's what it should be. Sorry, one. So, but as I mentioned, we can configure the size of the cache using some other numbers. So this example shows the same size cache, right? No, not same. So, but let's see this example. So this is the address field. Okay, this is the address field, and then you can find that the offset, the byte offset occupies 4 bits of the address field, which means the size of a single cache block is each 2 to 4, each 16 byte. Okay, each 4 word. Okay, so which means that the size of the single cache block is larger than the previous example, right? And then the index. So in this example, index field occupies the 6 bits. So which means this cache has 2 to 6 entries, 2 to 6 blocks. So this is the 64, right? So the size of the cache is the 2 to 6 multiplied by 2 to 4, which is 2 to 10, so which means 1 kilobyte. Okay. So using the index field and then offset field, we can figure out the size. So using the offset field, then we can figure out the size of a single cache block. And then using the index field, then we can figure out the number of blocks, which actually number of sets in the cache. And after we figure out the index field and the offset field of the graph, then we can also figure out the size of cache, the stored in the cache. Okay, 22 bits. So, and then using the index field and the offset field, we can also calculate the size of a single cache block. As I mentioned, when we mention the size of the cache, it means the size of data. Okay, size of data that can be stored in the cache. So this cache can store up to 1 kilobyte of data. Okay, this is cache size. So if we are interested in the CPU processor, then you can find the specification, technical specification of the CPU, and in this specification document, then you can find the size of the cache, size of the error cache, and cache, the processor. So using the data of the tag field, index field, and offset field, then we can calculate the size of, we can figure out the size of the cache block and the size of cache. So then let's discuss about the large block or small block of the cache. So in this example, so in the previous 2 examples, then the first example, the cache block size is the 4 byte. Okay, so example 1. And then in the second example, the cache block size is the 16 byte. Then why? Why is it different? Why? So what is the impact from the size of a block? So let us the cache size, the entire cache size is the 4 kilobyte. Okay, 4 kilobyte. So which means in the first example, this cache includes the 1024 blocks. Then in the second example, this cache includes the 256 right blocks, right? So even though the cache size is the same, we can compute the cache using the different size blocks. Okay. Then what is the impact from the impact from this cache block size? So I will explain about the larger cache block. So if the cache block size is large, so what is the benefit? So for example, let us assume that we are executing the load word for example, ops. So let us suppose that we are executing for I for 0, I as the 100, I plus, and then I equal BI plus CI. So this is the iterative loop, and then actually we can know that. So firstly, this program requires the A0 first, and then B0, and then C0, right? Because we require the A0 and B0, C0. And then the next iteration, and this program requires the A1, B1, C1, right? And then blah, blah, blah. So what is the benefit of the large cache block? So first, this data, the element A0, B0, and C0 are requested, and then initially the cache is empty. So the cache does not have any data. So in this, so which means that when this data is requested, then this processor encounter cache miss, right? So cache miss is encountered, then cache request the required block to the low-level cache or main memory. So which means if the block size is large, then this entire block is requested to the memory or low-level cache, right? Then in this case, in the example, cache example number 2, 16 bytes of data is requested to the L2 cache or main memory, right? And then the entire cache block is allocated. And then in the next iteration, then this program will request the A1. So what will happen? When the A0 is missed in the cache, then so A0 will occupy a part of this cache block. But entire, so 16 we will allocate this cache already allocate 16 bytes of data. So which means A0 will be here, A1 will be here. Okay, so what does that mean? With a large cache block, then we can utilize the spatial locality of our application, right? Because this is this program exhibits the spatial locality, right? Because when the A0 is at then we can know that A1 is at so A1 will be A1 is the neighbor of the A0, right? So if the cache block size is large, and then the A0 is missed in the cache, then cache allocates the large block, so 16 bytes of block, then the A1 is requested, and this A1 can be found in the cache. Okay, that is the benefit of a large cache block. So if we compare with the cache with the large block, then we can utilize the spatial locality observed in our application. That is the benefit of a cache. But actually in the real world, for maybe all systems have pros and cons. So if we use the large cache block, then we can utilize the spatial locality of our application. So what is the disadvantage? Right. That's right. So So when the cache miss detected, cache miss encountered, then this cache reaches the large data, the larger data. So which means that in order to provide this large amount of data from the low level cache or memory, it will take longer cycles. But now another disadvantage is cache has fewer blocks. So if the cache size is the same, the cache block size is large, then this cache will have fewer blocks. Okay, so in this example, the block size is 4 bytes, and this cache will have 1024 entries, and then the cache block size is 16 bytes, and then this cache has only 256 blocks, 256 bytes. The problem is that if cache block size is large, then this cache can only store 256 different data space, actually 256 different data blocks, okay? But if we use the smaller block, then this cache can store more different blocks. What does that mean? If we just handle a large amount of data, the large amount of different data, okay, like the A, B, C, D, blah, 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 G, and then A, B, B, G. So actually, if different kinds of data are handled by our application, then this cache, if a cache does not have smaller number of entries, then cache block can be already occupied by our many variables. Okay, so this is called the cache solution. Okay, so which means that our application is handling our application handling 1,000 variables. Okay, so and then actually we cannot observe any spatial locality among these 1,000 variables. So what does that mean? And then let us assume it is temporarily we can only observe temporal locality. So what does that mean? Our application is accessing 1,000 of different data space. But this cache, the cache example number 2, which has the large block, this cache cannot store thousands of different data space, right? So because the cache block this cache has only 256 blocks. So when this cache block is occupied by for 256 block, then for the 257th variable, then cache miss will be also encountered because this cache is already occupied by different thousands of data space. But for this cache can store the entire data space in this cache. Okay. So if we use the larger block, then the miss penalty. The miss penalty means that it's the required cycles for handling miss. So and then if the cache block size is larger, and when cache miss is detected, then the requested this cache is just the larger block. the large amount of data. So it will take longer cycles. So cache fetchment depth, this penalty will be increased. That is the first disadvantage of the large block. And then the second disadvantage is that cache can be polluted by many different data spaces. Okay, so because if the cache size is the same, the large block means that the cache has fewer number of blocks. Okay, these are the so actually so we will learn about the different configuration of the cache, and then you can find that pros and cons of the each configuration actually.
그것도 이거는 그러면 이 제로를 믿을 때이 제로부터 우리 평가에서 한 번에 표시해줘야 되는
그렇죠. 네. A0에서 이제 미스가 발생하면은 블록 16바이트를 채우기 위해서 리퀘스트를 보냈거든요. 그럼 16바이트가 다 채워지니까는 나중에 A1, A2, A3를 읽을 때는 캐시에서 발견이 되는 거죠. Okay, so I already explained about the cache is handling. So I'll explain. So actually in chapter 4, we learned about the 5-stage pipeline architecture of instruction fetch, instruction decoding, execution, memory, and write back. And then, as you know, the data memory is here. So, and then I mentioned that this memory is actually Aaron cache is Aaron data cache. Okay, and then we assume that the load instruction, like the load word is executed, and we assume that the data memory is accessed by load word, and then the data can be found in this data memory, right? In chapter 4. But because this data memory is the Aaron data cache, so which means that the request data can be found in the cache. It's the cache hit case, but the request data cannot be found in the cache. It's the cache miss case, right? So we just assume that the data is just found in this Aaron data cache in chapter 4. But it's not true, and then in reality, the data can be found or not. So actually, cache hit, so it's the hit, and we assume that it takes on one cycle, because so the data can be provided to the processor within one cycle. So CPU proceeds normally. So the pipeline is not stalled if the data hazard is not detected. So the pipeline is not stalled, but on cache miss, so load word, so load word is executed, and then load word access the data cache, the Aaron data cache, but the data is not found, it's cache miss. So in this case, this cache requests this data to the low level cache. Then it will take longer cycles. Then what will happen? So load word, this load instruction cannot be executed in the memory stage, right? Then the load word need to wait until the request data is provided from Aaron data cache. Now I already explained how the data prepared to be handled in the cache. Okay. So in this case, the data is requested to the low level cache, and then the data is allocated in the cache, and the data can be provided. So until the data is read from this Aaron data cache, the pipeline is stored. Okay. So in the cache miss case, load word waits in the memory stage until the data is provided. So which means that the following instructions are also stored in the pipelines. Okay. Actually, in chapter 4, I just explained this case, the cache case, but cache miss case is also considered the cache miss case. So think about this. The load word is stored in the memory, and then it will take a very long time until the data is provided to the load instruction. So it means cache, the performance of this cache or performance of memory hierarchy is very critical to the performance of processing. Okay, so entire pipelines are stored. Okay, and then actually, until now, so we just consider the load instruction. So which means that the data is read from the cache. Okay, data is returned to the cache, but this data is read from the cache. But we can also consider the store instruction, like store word. So think like this. In chapter 4, when the store word is executed, then just the data is stored in the data memory, right? But I said, oh, this is the one cache, not real memory, not the main memory. So we also just consider what will happen if the store instruction accesses on their cache. Okay, so store instruction. So when the load instruction is executed, load instruction just requests the data from the cache. So if the cache can just provide the request data to the processor, but store instruction is different. Store instruction update the data in the cache. Okay. So for example, AI equal B plus C. Okay. So let us assume that we are just to store the A0, and then cache block size is the 16 byte. So we just update the A0. So this when the processor store the A0, so actually this processor does not require data for A0, right? It just store the data, update the A0. Then it's a 16 byte. The cache block size is a 16 byte. So the processor executes the store instruction and for the A0. But let us assume that the A0 is not found in the cache. Okay? What will happen? Because so you can think then this is just update. But updated data is not found in the cache. This data will be in the main memory. Okay, the store instruction just update the main memory. But this data is not found in the cache. So what should we do? Actually, we can apply the different policies. The first policy is the write through. The write through means that the processor tried to write data to the main memory, but firstly, we just check the cache. Okay. Then, yeah, this data can be found in the cache or not. Okay. So let us assume that this data is found. So A0 is here. Okay. Then write through means that when the data is updated to the cache, then data is also updated to the main memory. Right? Understand? So which means in a processor, so this is the processor, then it's the error cache, then this is the main memory. So with the store instruction, then the processor try to store data to the main memory. This is the store instruction. But store instruction just actually the original purpose of store instruction is to update the main memory, to change the data in the main memory. Right? We learned that in chapter 2, the store instruction is data from the register file and then update the main memory. Right? That is the original purpose of store instruction. So write through means that when the store instruction is executed, then store instruction updates the data in the error cache, and at the same time, store instruction also update the data in the main memory. Okay? Then this policy is the write through policy. And what is the disadvantage of this write through? You need to remember that main memory is slow, right? So it means when the store instruction is executed, then this store instruction needs to update the error cache and main memory. Okay, so which means until this store instruction updates the main memory, then it will take very long cycle. Okay, that is the disadvantage of write through policy. Okay, so this is the example. It's not correct. It's not a precise example, but it can just estimate the impact of the write through policy. So let us suppose that the base CPI is 1, and then 10% of instruction are stored, and then write to the memory takes the 100 cycle. Because the baseline CPI is the 1, then the CPI is increased by its impact, the impact from the store instruction. So you can calculate the increased CPI by store instruction. So 10% of instruction is stored, and then the memory takes the 100 cycle. This is the increase the CPI by store instruction. So CPI is 11. It's amazing, right? Just because of the 10% of store instruction, the CPI is increased from 1 to 11. So 11 times slower than the ideal processor. So it's amazing, right? So actually, we cannot use the write-through policy using this configuration. So solution is the write buffer. Actually, if the write store instruction is the one direction instruction. So which means that actually the purpose of the store instruction is to update the main memory. Okay, but main memory is very slow. It's a very slow device. So instead of wait until this main memory is updated by the store instruction, we can add buffer. Okay, we can add buffer. So which means that store instruction just store the request to the main memory, and then complete its operation. And then the request stored in this buffer is processed one by one until the memory is available. Okay? It's similar to the storage. Storage in the logistics system. 그러니까 택배에서 물류 창고랑 비슷한 거예요. So storage in the logistics system. Because the customers are very slow, right? And then in order to wait until the process is completed by customers, because the customers are very slow, then the logistics system need to wait until the customer receives the product. It's very inefficient because the customers are very, very slow. What's the solution? The products are just stored in the temporarily stored in the storage system. And then these are delivered to the personal customer. So actually the same policy can be applied to the memory system because the main memory is very slow. So these requests are just temporarily stored in the right buffer. Okay. Then the store completes each operation. And then this request is one proceed to the main memory one by one. Okay. So using the right buffer, then we can also start the very slow operation of write through policy. Okay. And then another policy is the write back. So actually, most processors use this write back policy. So write back policy means that this is the processor, and this is the error, and this is the main memory. So when the store instruction is executed, then store instruction just change the data in the error cache, and that's it. The data is not updated to the main memory immediately. Okay? That is the write back policy. You may think it's ridiculous because as I mentioned, the original purpose of store instruction is to update the data in the main memory. But with the write back policy, the data in cache is only modified by store instruction, which is ridiculous, right? But with the store instruction, we need to update the data in the main memory. Then when this data in main memory updated, when is this data in main memory updated? So actually, when the store instruction is executed, then the store instruction just change the data in the cache. And this stored data, this cache data will be evicted from the cache. So in the previous class, you can find that, this is the stored data, but this data can be evicted if the request data is tried to store in the same cache block. Then the old data in the cache block need to be evicted. So it's removed from the cache, right? Because the cache is very small. So this block, the block in the cache will be evicted. So it's kicked out of the cache. So removed from the cache. Okay. But if this cache block is updated by store instruction, then this cache block is updated to the main memory. This is the write back policy. Okay. So instead of update the main memory immediately, the store instruction just update the data in the cache and then just mark that, oh, this cache block is updated. And then this mark is called the dirty bit. Okay. So like the valid bit, so this is the control cache control bit. When the store instruction is executed and then the store instruction change the data in the cache, then the processor just mark the dirty bit as 1. So which means that, oh, this cache block is updated. So the cache block contains the changed data. This data is changed from the original data because of the store instruction. Then when this block is evicted from the cache, it's removed from the cache, then this block is updated to the main memory. This is the write back policy. So even though store instruction is executed, then the store instruction just change the data in the cache only. Okay, the store instruction does not update the data in the main memory immediately. And then actually this update is performed when the cache block is evicted. The block is evicted from the cache. Okay, so this is the lazy update. And then what most processor employ is write back policy. This is because think like this. A0 go B AI go BI CI. So when this data is updated in the cache, and then we assume that this data will be used by other statement like the TI equal AI plus 1 like this. So because of the temporal locality of our program, the updated value also can be re-referenced by our application. So in this case, then write back policy is better. Okay. So actually, we can also start this long latency of the store instruction using the write buffer. Okay. It's possible, but usually most processors employs the write back policy. Okay. So you can understand there are two kinds of write policy for the store instruction. The write through policy, the memory is updated immediately by store instruction, but the write back policy, the store instruction just update the cache block and then just mark the dirty bit for the corresponding cache block. And then if this cache block is evicted from the cache, then memory is updated. Okay. So this is the write back policy.
블락 사이즈가 16바이트,
네.
코어를 4바이트만 PC A0, A1 이렇게 이렇게 있는데 A2만 코어를 했을 거면 A2만 딱 붙을 수가 있어요.
그렇죠. 뭐 그럼에도 불구하고 모든 블락을 업데이트를 합니다. 항상 그 캐시에서 데이터가 없다는 것은 블락 단위로지 왔다 갔다 하기 때문에 더티빗을 블락 단위로 존재하고요. 그러니까는 뭐 다르게 이제 설계를 할 수도 있긴 하겠지만 보통은 더티빗을 we have only one dirty bit per block, so which means that dirty bit is marked and entire block is written back to the main memory. 한꺼번에 다 업데이트해요. 블락 사이즈 다. 뭐 상관없잖아요. 오리지널 그 업데이트가 안 된 거는 그냥 메모리에 써있을 거고 업데이트 되거나 체인지드 밸류가 업데이트가 될 거고 문제는 없습니다. 엔타이어 블락이 업데이트가 되는 거죠. Okay. Also, we can think of another case, which means that it's right miss. So, right miss means that when the store instruction is executed, then the requested data, this data block is not found in the cache. Then you can also consider the two different policies. So the first policy means that it's like the AI equal P plus C. So I mentioned that in the right miss case, then this data AI is not found in the cache. But we already know that store instruction does not require original data for AI because the AI is updated by P plus C. Okay, so it's a new data. So, but when the store instruction try to update the cache, then this data is not found in the cache. Now, what should we do? The first possible policy is the write around. The write around means that, oh, we just updated this block, okay, or this value. Then this request is just bypass the cache because the cache does not have the AI, this value, this data, and then we don't need to actually, the processor does not require original value of AI. So in this case, this store instruction bypass the cache and then update to the request is given to the low level cache or memory. This is the right around policy. But we also consider the allocate on miss. So allocate on miss means that when the store instruction try to update the AI, but this is the right miss. So which means that with the address of AI, then we check the cache, but this data is not found in the cache. So in this case, right allocate on miss means that the request for this block allocation is given to the low level cache or main memory. Then the data is returned to the cache, and then the cache allocator is return data to the target block. Then this block is updated. So this is the right miss key. So actually, the previous example is the right through and right back is the right hit case. Okay. So when the right miss, then we use the allocate to miss policy, then if the right miss is detected, then entire block is requested to the low level cache, main memory, and then this block is allocated to the cache. Then this block is updated. Okay. This is the allocate on means, and then write around means that the write does not require all the data. So just to write to allocate. In the write miss case, then store instruction just bypass the cache. This is the write around. But in the write back policy, we normally use the allocate on miss case. So it is because when the write is performed, AI equal PI plus CI, then the firstly we can think that when when the data is written to the main memory, but as I mentioned, we can use this data also, right? So which means that with the temporal locality, because of the temporal locality, this written data will be frequently used, very frequently requested. So if this data is far in the cache, then we can also reduce the latency for the request data fetch. Also, if the AI, some data is used by store instruction, so which means that even though the write is detected, and if the entire block is allocated to the cache, then we can also utilize the spatial locality. Okay. So actually, for the write specs, if we use the write spec policy, then it's normal. But we can select the other policy. We normally use the allocate on this policy. Okay. So I will skip this example. Okay, then let's. Oh, the 47. Okay, so I think I need to stop here, and then in the next class I will explain about the cache performance. Okay, so actually, so I will just briefly explain. Because of the cache is the small memory, so we cache has the two different events, like hit and miss. So which means that because of hit and miss event, the performance of cache is also influenced by the ratio of hit or miss events. Okay. So in the next class, I will explain about the cache performance by cache events. Okay. Okay. So any question? Thank you for your attention, and then see you in the next class. 감사합니다.